In this video, I'll walk through the proof of Theorem 3.28, which proves that Kruskal's algorithm always produces a minimum spanning tree when given a connected weighted graph. So let's see why Kruskal's algorithm really does spit out minimum weighted spanning trees. Let me take a second to remind you of Kruskal's algorithm. Remember, the idea was we start with the graph G, and we add edges to the vertex set selected from the edges of G of minimum weight and such that that edge does not produce a cycle with the previously selected edges. So we keep adding edges of minimum weight in the edge set of the graph unless that edge produces a cycle, in which case we won't add it, and we'll look at the next minimum weight. So why does this produce a minimum spanning tree? Well, let's prove it. So we'll start by letting T be a spanning tree of G. G is our connected weighted graph obtained by Kruskal's algorithm. Seems like a natural place to start. And we will assume, to the contrary, that is not a minimum spanning tree. So yeah, what would happen, what would be the case if Kruskal's algorithm did not spit out a minimum spanning tree? We'll show that there's some contradiction that arises from this. Let me be a little bit more specific. Instead of it, I'll say T is not a minimum spanning tree. So just like we've done in the past, I'll choose a minimum counterexample. So, well, yeah, essentially that is what I'm doing. So let's see. Let's also suppose, let's give ourselves some edges for T here. Let's say the edge set of T is equal to these set of edges, E1. I'm going to label these and order them in the order in which they were selected from Kruskal's algorithm. So that is, I can know for sure that the weight of edge 1 is less than or equal to the weight of edge 2, right? So I have these in non-decreasing order. And I know I have n minus 1 of them. So I should have said somewhere G of order n. Then I know exactly how many edges any spanning tree will have. It'll have n minus 1 since it's a tree. And since T was spit out by Kruskal's algorithm, I have this non-decreasing sequence of weighted edges. And we're supposing that this is actually not a minimum spanning tree that Kruskal's algorithm put out. So I'm going to choose, it means there must be a minimum spanning tree sitting out there, right? There has to be some minimum spanning tree. So of all those minimum spanning trees that aren't T, of all minimum spanning trees, select one, let's call it H, that has the most number of edges in common with T. So let's find essentially the closest one to T in terms of the number of edges it has in common with T. So what does this mean? Well, we know that H is not equal to T, otherwise T would have been a minimum spanning tree. And so there is some edge of T that is not an H. There is some edge of T that is not in H. And I'm going to call this special edge E sub I. So let E sub I be the first, in terms of its index, the first edge of T that is not in H. All right, so what I'm going to do here is I'm going to construct a new tree that has the same weight as H, this minimum spanning tree, this minimum counterexample. So I want to construct this tree, has same weight as H, but with more edges in common with T, and that's going to be my contradiction. So how do I do this? Well, what I'm going to do is I'm going to add this edge, E sub I, to H. So let G naught equal H plus E sub I. So I'm adding this edge to H. H was remember E sub I was the first edge of T that is not an H. And so H would have n edges. And so it'd be unicyclic, it would have one cycle in it. But G naught equal H plus E sub I. Then G naught contains a cycle, C. And since it has a cycle, that means I'm going to need to, if I want to construct this tree with the same weight as H, that I'll be able to find another edge to remove from G naught. So let's see. We know that T doesn't have a cycle. Since T has no cycle, there is an edge, E naught, on C that is not in T. Right, so I added this edge that was in T, right, E sub I is in T, to H. That produced a cycle. I'll look at that cycle, and I know that since T doesn't have a cycle, there's some edge on that cycle that's not E sub I, and moreover, it's not in T. So this edge E naught is not in T, and what I'll do is I'll remove it from G naught. So let T naught equal G sub naught minus E naught. So notice this is really the same as saying that I did H, I added this edge E sub I, and then I subtracted this edge E sub 0, E naught, from it. And then this must be a spanning tree. Right, I just removed an edge from a cycle of G naught, which was spanning, and so it must still be a spanning tree. And my claim, so let me be clear about what I'm doing here. My claim is that the weight of T naught is the same as the weight of H. And notice what I've done here is I've added E sub I, which was in T, and removed E naught, which was not in T. And so the edges of T naught have more edges in common with my original tree T than they did with H. And this will be a contradiction, which would be a contradiction. Again, because it would have more edges in common with T than H did, and H was selected to be the one with the most number of edges in common of all minimum spanning trees. So, right, if I can show this, the weight of T naught is the same as the weight of H, this means, right, this would imply that T naught is a minimum spanning tree, and that would be my contradiction. So I need to show this. And this is going to go to how Kruskal's algorithm is designed. It's always designed to choose edges of minimum weight that don't produce a cycle. So keep in mind here that the weight of T naught is the weight of H plus the weight of E I minus the weight of E naught. So we know H was a minimum spanning tree. So we know that since H was a minimum spanning tree, I hate how it does that. H was a minimum spanning tree, it follows that the weight of T naught cannot be less than the weight of H. So we would have that the weight of H is less than or equal to the weight of T naught. But that's the weight of H plus the weight of E sub I minus the weight of E sub 0. So we can cancel these H's out and see that weight of E naught is less than or equal to the weight of E sub I. So we can eliminate one case right here. That is, if E sub I, if the first edge of T that was not an H was I equal to 1, we can eliminate that case. So let me say, so if I were equal to 1, well, then we can say that the weight of E naught must have been equal to the weight of E sub I, which is 1, I equal to 1. Right, because, let me just say in parentheses here, right, otherwise, E sub 0 would have been chosen first. Right, if the weight of E naught was strictly less than the weight of E1, we would have chosen that first. Kruskal's algorithm would have grabbed that one first because E1 would have the smallest weight of all the other edges that are in T. So that would have been chosen first, and so we can say for sure that these must have actually been equal. Now notice what happens if these are equal. Then the weight of H would be the same as the weight of T naught, and we would be done. That would prove my claim that these weights are the same and arrive at a contradiction. So we can assume I is strictly greater than 1. But we'll still run into an issue here. So what I'll say is, consider the I minus 1 step in Kruskal's algorithm. So that is, we're building this tree T in Kruskal's algorithm, and we already have the edges E1, E2, up through E sub I minus 1 have already been selected. And we know that since E sub I was actually added in Kruskal's algorithm, if we finish this out to obtain T, EI can be added without producing a cycle. Right? And this is indeed what happened when T was produced. But also, but E naught could also have been added. Could also have been added without producing a cycle. So what that means is that the weight of E sub I must have been less than or equal to the weight of E naught. Of course, we already know that the weight of E naught is less than or equal to the weight of E sub I. So we can say that the weight of E naught is actually equal to the weight of E naught. E sub I is equal to the weight of E naught. Then the weight of T naught must be the same as the weight of H. So T naught is also a minimum spanning tree. But remember how we got T naught. T naught was chosen. It had more edges in common with T than H because I added this edge E sub I, right? T naught contains E sub I, and E naught was not in T. So T is also a minimum spanning tree with more edges in common with T, which is a contradiction. And that finishes the proof. So this is exactly why Kruskal's algorithm works, why this idea of just adding edges of minimum weight that don't produce a cycle will work. And it's exactly in this proof. All right, so that's it with this video. See you next time.